So. Started. All right, so today's form of analysis that we are looking at is failure mode and effect analysis. So the FMEA is one of the two analyses that we'll be focusing on in this course. It's one of the ones that you have as an option for the type of analysis that you will use for your final project. If you choose to research and analyze a piece of equipment or machinery, the functional FMEA will be the analysis that you will utilize for your project. The failure mode and effect analysis is one of the most familiar of the system safety analysis techniques in use. It has remarkable utility in its capacity to determine the reliability of a given system. So the FMEA is an analysis that specifically evaluates a system or subsystem to identify possible failures of each individual component in that system. So where before, when we were looking at subsystem hazard analysis, we were only looking at one portion of the subsystem. With the FMEA, it looks at kind of the overall system and all of its subsystem parts together. So it looks at the greater importance of the overall system safety effort and attempts to forecast the effects of any such failure. So again, looks at the whole system and all of its subsystems, and looks at the most important part of this one is it looks at failure mode. If something fails, how is it going to affect the rest of the system? So because the FMEA's ability to examine systems at the component level, potential single point failures can be more readily identified and evaluated. The two basic types of FMEAs are distinguished more by the target of the analysis than the actual analysis itself. In fact, the systems required in the performance of each are very similar, and only the items that are being analyzed is the difference. Okay, so the two types are going to be functional FMEA and the hardware FMEA. So the functional FMEA utilizes a deductive reasoning approach. It begins by assuming a failure and focuses on the modes that could cause that failure. So we start off with looking at all the potential ways that the system can fail. Deductive reasoning. In the process of deduction, you begin with some statements called premises that are assumed to be true. You then determine what else would have to be true if that premises is true. Okay, an example of deductive logic: all men are mortal. Joe is a man, therefore Joe is mortal. So it's kind of those linking type statements where, like, if this is true, then this also has to be true. So if this is true, then that third thing is definitely going to be true as well. So if the two statements are true, then the conclusion could be that Joe is mortal, right? Bachelors are unmarried men. Bill is unmarried, therefore Bill is a bachelor. Okay. The functional FMEA targets any subsystems that may exist within an existing system. So up to this point, it encompasses subsystem safety analysis. Like, for example, if we were to look at the RMS Titanic, you guys know that when it went down, it didn't go down just because of one thing. It was kind of one subsystem that failed that led to another system that failed and another system that failed, and eventually the whole ship goes down. Any of you guys familiar with the Titanic? What caused it to go down? It hit an iceberg, right? But did just hitting that iceberg cause it to go down? What happened after it hit the iceberg?
Didn't they like tell them not to go that way?
Right. They shouldn't have been going as fast as they were going in the first place, but they also, because of all of the ice that was in the water, the poor lighting at that time of day and things like that, it was difficult for them to see. So when they did finally see the iceberg, they called to make the turn, but the ship is huge. It's not going to be able to make a turn that quickly. So instead of hitting head on, they did make a bit of a turn, but it caused it to gouge down the side of the ship. And when it did that, because the rivets and the metal were a lot weaker than they should have been, because they rushed the processing of building the ship to start with, it rips through and goes ahead and lets some water start pouring into the bow. And once it poured in, if it had just filled the front chamber, they would have still been afloat. But the bottom part of the ship is broken into several different chambers. And each one of them is supposed to have a bulkhead that goes all the way to the top and seals off so they can close one chamber from the next and prevent water from filling the whole bottom of the ship, right? but they didn't build them all the way to the top and make them sealable. So water then just pours over one into the next and then over into the next, and that causes the ship to start tipping forward until it's so heavy that it breaks off. And then of course it's going down once half of it has broken off. So if there were many different things that if they had built it the way it was designed, it most likely would not have gone down. It would have probably had some damage, but it wouldn't been nearly as catastrophic as it was. So when we're looking at this type of analysis, we're looking at all those little subsystems, and if this one fails, how is that going to affect the next one? So that we can see kind of what would the chain reaction be for the overall system. Ideally, so that we put those systems in place like what was initially in the design of the Titanic, if they had done those other things and thought about the possibility if this happens, then this, then they could have prevented that overall failure from occurring. Okay, so the analysis not only looks for the possible effects of subsystem failures on the overall system, but also examines the effects of such failures on other subsystems within that system. So this is one of those really comprehensive analyses where some of the others, they've been just little bits and pieces where we look at the operator, we look at a subsystem and all that. With the functional FMEA, we look at everything all together and how each one could potentially affect the other. The fact that it examines multiple subsystems is what differentiates it from subsystem analysis. So the subsystem, again, just looks at one of those subsystems, where this one is going to look at all the different subsystems and their interactions together. When a complex system, such as a nuclear reactor, airliner, an overhead bridge crane, or a new robotic milling machine, consists of numerous secondary subsystems, each with its own set of supporting subsystems, the functional FMEA should be performed to ensure proper system safety evaluation at every level. The hardware or detailed FMEA uses the inductive reasoning approach. So this is the other one that we just talked about was the first type of FMEA. This is the second type. Inductive reasoning means in the process of induction, you begin with some data and then determine what general conclusions could logically be derived from that data. So in other words, you determine what theory or theories could explain the data. So think back to when we were talking about the chapter about statistics and probability. The first type of FMEA that we're looking at is going to look at more of the statistical data, the stuff that has already happened, where this one is looking more at the probability of what could potentially occur. Okay, so for example, you note that the probability of becoming schizophrenic is greatly increased if at least one parent is schizophrenic, and from that you conclude that schizophrenia may be inherited. Okay, inductive reasoning. That is certainly a reasonable hypothesis given the data. However, induction does not prove that the theory is correct. It just leads you to believe that based on what has happened previously, this is what we could conclude may happen in the future. Inductive reasoning, there are often alternative theories that are also supported by the data. For example, an environmental factor may cause the child to be schizophrenic, not the genes themselves. What is important in induction is that the theory does indeed offer a logical explanation of the data. So it can't just be random thoughts about what might occur, but it's going to be based on the data that is currently available that indicates that this may be the cause or this may be what will happen in the future. To conclude that the parents have no effect on the schizophrenia of a child is not supportable given the data and would not be a logical conclusion. Okay, so an example of inductive logic. This cat is black. Or this cat is black, that cat is black, a third cat is also black, therefore all cats are black. That obviously would not make a reasonable assumption. Just because every cat you have seen personally is black doesn't mean that every cat that ever exists is going to be black. So we want to make sure that when we are making these inductive reasonings or these conclusions about what could happen, we're looking at previous data, but not eliminating all other possibilities of things that could occur. The hardware FMEA recognizes common failure modes and examines the effects of those failures on the entire system, its subsystems, or just one subsystem, depending on the type of equipment that you're looking at, the process that you're evaluating. The The hardware FMEA examines actual system assemblies, sub-assemblies, individual components, and other related system hardware. As with the functional FMEA, the hardware FMEA evaluates the reliability of the system design. It attempts to identify single point failures as well as all other potential failures within a system that could possibly result in failure of that particular system. So, disadvantages of the FMEA. First, it does not typically consider the ergonomic elements, only the system itself. So it's looking at the actual components of the piece of equipment or process and not necessarily at how the person is going to interact with it. It purposefully omits multiple failure analysis in the system, which means many failures happening all at once. So it only looks at each kind of systematically, each potential failure and what that would occur down the line, rather than looking at if we had two or more things go wrong at the same time, how that would affect the overall system. Third, it fails to evaluate any operational interface. Again, that kind of goes back to the ergonomic situation. It doesn't look at potential human error that may enter into the system. It only looks at the failure of the components within the system. And it requires consideration and evaluation of any known components, failure rates, and other similar data. So really, to do an effective FMEA, we need to have data available on failures that have previously occurred. So steps in performing an FMEA is first gather the data, because like we just said, you got to have the data available. You got to know how frequently parts of a system are going to fail and how they fail in order to analyze the system using this type of analysis. We need to establish the scope of analysis. Are we looking at all the systems, just certain subsystem interactions? How far are we going to go with the analysis? Examine the effects of the specific failures in that system or subsystem and how they're going to interact with each other. And then record the analysis on the FMEA worksheet, which I'll show you here in just a second. And it looks very similar to many of the other worksheets that we have seen previously in this class. Okay, so the failure mode and effect analysis, we have part or drawing number. So we're looking at the schematics of whatever the equipment is. We've got that part's name, its specific function, failure mode and cause. So what would it look like if that piece were to fail and what could cause it to fail? Failure effect on the system or the component. So if this fails, what is that going to do to that system or subsystem? Its effect on job or personnel, and then the criticality level is going to be the same as the risk assessment matrices that we've looked at before. So we're rating it on possibility and likelihood that it's going to occur. Or I'm sorry, severity and likelihood that it occurs. Okay. In the functional FMEA, if we're looking at this one in your final project, what you'll do is describe the overall system, the system and how it operates, its failure modes, causes and effects, and give criticality assessments to each, and then give conclusions about how all of those different parts are going to work. And that we'll talk about in more detail when we get to talking about the project. Not next week, but the week after, we'll be introducing the final project for this class. All right, sections of the FMEA report, introductory information. So when we do the, just like with all the others, when we work out that worksheet, then the next thing that we're doing after that is putting together the assessment report that has greater detail than just the worksheet itself. The worksheet just kind of breaks down what you need to be talking about. And then the report is going to give your complete analysis, your explanations for why on probability and severity and why things would fail in the way that they would, all of that kind of information. Okay, so we would start off with the purpose and the scope of the analysis so that if other people are reading this in the future, they know specifically what it was that you were looking at with your analysis and the scope of that. So how much of the overall system is included in the analysis that you did? Is it just two subsystems and how they interact with each other? Is it a variety of different subsystems? Is it the entire system and each of its subsystem components? So give us a description of what the scope is. The limitations of the FMEA, and limitations may include things that you have limited data that is available to you, a limited time frame to analyze the event or the equipment failures because maybe it's a new product and it hasn't been out there for very long. So we have very limited data that's available. We don't have kind of a lifespan of the equipment type analysis yet, okay? Types of FMEA conducted, whether it's functional or hardware FMEA. The methodology used, which is going to include how the FMEA was performed by the team. So if you looked at each subsystem individually and you got the full description of each one, and then you looked at one in comparison to another, and then that one in comparison to another subsystem, that's the kind of thing you're describing in the methodology. How did you compare the subsystems and or the overall system? Evaluation of any past lessons learned, anything that has previously been learned, and this doesn't have to be just within your own organization. This could be other organizations that use the same types of equipment that you are evaluating for this particular FMEA, okay? And then ground rules established by the safety professional for performance of the FMEA. This is going to be any kind of additional information that you might need related to that FMEA and your team and how they did this analysis. Okay, section 2 will include definitions. These include phrases that may not be familiar to the management team, or if you're using any kind of acronyms, you'd want to describe them out in this section. System description is going to depends upon information that is available to you, but you're going to give a full description of the system, explain its intended functions, explain the system components, each of the little parts that you're evaluating, explain any required interfaces with other components or other systems and how those interactions occur, and then use caution in terms of your level of detail so that the readers will not be confused. You want to make sure that when you write this out, the tendency for a lot of people is to just kind of brain dump on the paper. Make sure that once you spell that all out, you think about if somebody had never seen or interacted with this system before, would they be able to understand what I'm saying based off of the description that I gave? And it's usually a good idea that when you write up these evaluation or the descriptions, that you then have somebody else read it, especially if you can find somebody who isn't familiar with it, so that they can read it and see if they understand it, because you may need to add a little more detail or clarification to it to make it easy for anyone who might be reading that in the future to understand. Criticality assessment, detail the level of the system, subsystem, and component criticality, usually based on some predetermined criteria that have been agreed upon by management. Like I said, most of the time people are just going to use the risk assessment matrix like we've talked about on all the previous assessments. Really the easiest way to do systems analysis within your organization is to pick one risk assessment matrix and agree upon what the definitions of each level are. It doesn't have to be the one that we presented in this class. There's like hundreds of different options available out there on the internet. Just make sure that whatever analysis that you're using, that you're looking at, you're calling the same thing by the same term. So for example, if you're calling it critical, everybody should be able to agree that critical means either we're killing somebody or we're killing the system. Okay, everything's going down if we're calling it critical. Or if it's minor, what does that mean? So it doesn't necessarily matter what those definitions are so much as it matters that everybody's working off the same definition, okay? But once that's agreed upon, and like I said, I just recommend use the same risk assessment matrix for all the different analyses. Get that criticality assessment, so it might be like a 3A or a 2B or whatever it might be, okay? With the criticality, this is going to give an expression of concern over the possible effects of failure in the system. If any failures could result in adverse effects on personnel, such as death, injury, illness, or equally undesirable effects on our equipment components or the subsystem or the system itself, such as system loss, equipment damage, etc., then the level of criticality will reflect that assessment. So you give it the letter and number assessment, and then describe why you've assigned that to it. Okay, what is the level of criticality? How severe will it be? And then how likely is it that that's going to occur? Okay, in the worksheet in figure 10.4, there is the rating designated on the scale. The rating that I used for this example is 1 equals most critical, 3 equals less critical, 2 is somewhere in between, okay? Discussion of criticality assessment details and acceptance or rejection of criteria or process that the team used to justify any of its recommendations. Okay. And the last part of this report, the documentation list. a list of documents that the safety professional may review or reference during the FMEA. This is usually like if you've ever looked at one of these kind of reports and you look in the appendices and it's got the drawings, the schematics, the worksheets and things like that. That's the kind of stuff that would go in your documents list. So it would be a list of all the documents that you use, system specification, operating procedures, schematics, any kind of vendor documents that you might have from the manufacturer, like the operations manual, anything like that, that would go in the back, okay? And then, I'm sorry, there is another section, 2 more sections after that. The data section is supporting data such as photographs, layout, drawings, electrical schematics, FMEA worksheets, any kind of additional stuff that went along with figuring out the information that you used for the report. And then critical items list, this is a list of any and all items within a system that if a failure were to occur, would have a critical effect on the operation of that system. This is going to be the list that provides a detailed descriptive information on each item. This may be things like you have to change out this part every 3 months, or there's the potential for full system failure. It could be that, you know, this one component needs to be inspected every single day before startup to make sure that it is in good operational order, because if this one component fails, the entire system will fail, or it would be a life-threatening result if it failed. Okay, so this list is going to provide those details that describe that information about each element that's considered a critical piece of that system. It explains each item's overall function of the component that make up the item in question. The failure mode that is determined to be critical is then listed along with the potential effects of that failure. If the safety professional states that an item on the critical items list is to be accepted as it is, then the safety professional must provide an explanation as to why it is acceptable. Okay, if it is deemed that it would not be acceptable, then you're going to put in the requirements that make it become acceptable, like what kind of control measures need to be in place in order for it to be at an acceptable level. Okay, this example will develop a hardware FMEA for a process system that is well into the design phase of the product's life cycle. The nature of an FMEA requires evaluation of subsystem, sub-assemblies and or components. For this reason, more detailed and specific description information is provided here than that supplied for previous examples that we've talked about. Okay. So let me turn off the light up here so you'll be able to see the picture a little bit easier. What we're looking at here is a overhead crane system. Okay, although the overhead bridge crane example in your text follows the exact order the FMEA report presented previously, we're going to be jumping ahead on that report and looking at the overall analysis. Okay, so we'll begin with the system operation. We'll begin with this section so that the class can have a better understanding of the general function of that overhead crane. However, for those of you performing this functional analysis over a piece of equipment for your final project, you want to make sure that you do cover all of the sections that are in that template. Okay, so system operation. The overhead bridge crane system described above is used to transport precast fiber speedboats and light fishing craft from their final assembly location into a manufacturing facility onto a transport vehicle, which is usually a flatbed truck that has been backed into the facility. The operator must control the crane movements with the precision required to lift, transport, and lower the boat into place on the transporter. The hoist trolley design configuration will allow a travel span of 14 feet laterally, so from side to side, which provides ample operating flexibility when positioning the hook over the load, as well as when lowering the load into position on the truck. The longitudinal runway travel length is 20 feet, also provides the operator with discretion or discretionary maneuverability during the crane operations. The main hoist is used for movement of the boat themselves, while the smaller auxiliary hoist is used primarily to handle individual components being installed on the boat. For example, seats, windshield, dashboard, things of that nature. Okay, so the big crane itself is used to pick up the boats and move them. The smaller crane that is a part of the subsystem is going to be used to pick up and move smaller components that would go in the boat. All right, all on the same page there before I move on. Okay. All right, so the system component, subassembly description, the subsystem that we're looking at is the hoist assembly in the picture that we have up here. The overhead crane in this example consists of 2 hoists, a main hoist of 10-ton capacity and an auxiliary hoist of 1.5-ton capacity. Okay, so the big one that can pick up the 10 tons, that's gonna be the one picking up the boat itself. The one that has the 1.5 ton capacity would be the one that picks up smaller components. The crane has powered trolley and bridge drives with control from plug-in type floor console. This crane will operate within a manufacturing facility that produces speedboats and small fishing craft. The crane is manufactured and will be installed by the XYZ Crane Incorporated. Figure 10.2 shows a simplified layout of the crane system. The 10-ton main hoist assembly contains 2 main hoist motors, a 30 horsepower main hoist AC motor, the main hoist magnet torque load brake, the main hoist gear reduction assembly, and the wire rope drum assembly. The 1.5-ton hoist assembly contains the same components as does the 10-ton. However, the auxiliary hoist motor is rated only at 18 horsepower and a single auxiliary hoist brake is provided. Okay, so components, the electrical hoist motor and control, both hoists have enclosed, non-ventilated 220, 440 volt, 3-phase, 60 hertz, 1200 RPM motors. The control used on the hoist motion is referred to as the static stepless magnet torque control on the manufacturer's drawings. With this control, the drive motor torque is controlled by means of fixed resistors and saturable reactors in the motor secondary circuit. To obtain very low speeds with overhaul and light loads, an electric load brake magnet torque is coupled to the motor shaft. Okay, so basically, what they're telling you there is you have, with that motor that you see up in here, you've got the motor itself that's going to cause the hoist to go up and down. You have a braking system in there that causes it to stop moving when you want it to stop. And then also it's got the crane mounting structure itself that allows it to go forward and backward, right to left, so that you can position things where you need them to be positioned. Okay. All right, there are 2 magnetic amplifiers, one responding only when the motor speed is above that called for by the induction master. Okay, and the other when the motor speed is below that called for by the induction master. Normally, in the neutral or off position, the magnet torque load brake is fully activated. During crane movement, whenever the motion is slowed or stopped by moving the induction master handle toward off, the magnet torque load brake provides braking torque that slows down the drive before the motor brake. This reduces the wear on the motor. So instead of just a hard stop, it slows it down to a stop. So it's not going to stop immediately. Okay. And then the other component that it talks about is the magnet torque electric load brake. I'm not going to read you every word that it says on there. Okay. But basically you get the idea. You give a description of what's the overall system that you're looking at, each of its component, a description of what each of those components does. Okay. This page gives you more description because it's talking about the motor brake assembly, the hoist gear reduction assembly on the wire rope drum. So what causes the wire ropes to go up and down, the motor driven power wheel, trolley driver assembly, and then the bridge drive assembly itself. So it's talking about the remaining components that we haven't discussed. Okay. Subsystems in this, we have a subsystem is the control station, which is going to have the operator's controls on it. The hoist control is accomplished from a plug-in style floor console that contains the following components: the main and auxiliary hoist control, bridge and trolley controls, stop start push buttons, selector switch, which is the major controller that turns it on and off, run inch push button controls, and warning bell push button. Okay. Another subsystem that it has is for the 1.5-ton crane, the micro drive system during micro drive operations. which is when it's going very slow. An electric clutch is used to engage the micromotor and associated gear train. Okay, passive components. These are other components that they don't actually do something, but the rest of the system uses them to do stuff. Like, for example, the wire ropes. The wire ropes themselves don't necessarily do anything. They don't have any action of their own, but they are used as a part of the system. The hooks, the wire ropes, load blocks, sheaves, suspended frame assembly, the drum gears, trolley and bridge shafts, all those different components that are basically stuck in place. They don't have any energy drive in and of themselves. Okay, failure modes and effects. So the next thing that we look at is how could any of these components fail? So at face value, on the basis of the information provided, the complexity of the system described above appears to offer numerous opportunities for critical single point failures. So any point where if that system were to fail is going to cause either the crane to fail, cause us to drop the load and damage the product that we're trying to work with. Okay, so therefore the analysis should begin the FMEA process by first attempting to identify any and all non-passive components and or subassemblies that, depending on the type of the mode of failure, could possibly have an undesirable effect. List each identified subsystem or related component in the overhead bridge crane system used in this example. So some of the examples that they show you in the book of the things that could fail, the hoist assembly, and that includes the hoist motor brakes, 30 horsepower hoist motor for the bigger crane, the 18 horsepower hoist for the smaller one, the Magnetorque load brake, hoist gear reduction assembly. With the electric hoist motors, we've got fixed resistors, statable reactors, motor secondary circuits, induction masters, magnetic amplifiers, motor shaft extension, and the system, it just goes on. So you've got each of the subassemblies and then all the components that are within that subsystem. Okay, and then you put those into your worksheet. So you have each of those parts that we just had, the ones that were listed here, each of the different ones. Well, then we're going to list them out here. So we got the main and auxiliary hoist motor, provides motivation power for raising and lowering suspended loads from the hoist. Its failure mode would be loss of power, defective circuitry, or defective bearings. Those things would cause it to stop moving. Okay. Load cannot be raised or lowered. The brake would hold the load stationary if this were to occur. So this part over here is going to tell you what would be the effect on the overall system if this failure happens. Okay. The effect on the job or operation, no effect except the delays, because if it locks itself in place, they're not going to be able to raise, lower, or move it forward or backward, right? And the criticality level they put on that is 3, because if you remember, 1 was the highest level, 3 was the lowest level. There's no damage. It's just going to stop work from being done if that were to happen. Okay. And so I'm not going to read you all the different ones, but you can look at this example in your textbook, and basically it's going to go through each of those items that was listed as having a critical component. If this thing fails, work can't be done, or something is going to be destroyed, whether that be the system, we drop the boat that we're trying to move, those kind of things. Okay. In the failure mode effect described above, one failure mode has been assessed as critical. The analysis should not provide either acceptable or rejectable rationale. I'm sorry, the analyst should provide either acceptable or rejection rationale, so the management can evaluate all aspects of their failure mode effect before making their decision. So in this example, the following acceptance rationale is suggested. First, let me go back to the one down here that was critical, was the main hoist gear reduction assembly. Transfers the motor and braking torque and provides for mechanical advantage through gear reduction from the motor to the hoist drum. If our failure mode and cause for this structural failure of the gears, pinions, or keys, the effect would be torque necessary for lifting or holding the load would be lost and the load would be dropped, which this would be potentially the load is somebody's boat, right? We don't want to drop that because that's going to cause damage. Okay. The effect of the job or personnel, possible loss of life or serious injury, damage to equipment. So this one is going to be considered a 1. It's critical. If we do that, we kill somebody or we destroy the product that we're trying to work on. All right. So the rationale that we give for making that one critical is an operational check of the hoist will be performed prior to each use to verify the proper operation of all gears. Such pre-operational functional tests will exceed the minimum acceptable test required by OSHA 29 CFR 1910-179. Preventative maintenance inspections will be conducted weekly to ensure proper gear, pinion, and key operations. This periodic inspection interval will exceed the minimum monthly inspection required by OSHA because we're doing it on a weekly basis instead of monthly, okay? Probability of failure is considered remote on the basis of the following design considerations. Shaft and gear design will be in accordance with standards established by the American Gear Manufacturers Association. The minimum design safety factor for this gear will be 5 to 1. The gear will turn in a continuous oil bath that will dissipate friction, heat, and lubricate the gear bearing surface. Hook over travel will be controlled by an upper limit switch, and disengagement would require structural failure. The most probable result of structural failure will be binding and or noisy operation that will alert the operator and those in the general vicinity of the problem with the crane. So as you can see, they're explaining all the different things that can be done to prevent failure of that system. 4, a load test of the hoist at 125% of its rated load will be performed annually. This annual test will exceed the minimum requirement for only an interval load test as specified by OSHA 29 CFR 1910-179. And there is no significant documented failure history for this type of equipment. In fact, standard industry reliability handbook establishes a generic failure rate for gears of 1.67 failures per million hours of operation. So this is all of their justification basically for operating the system as is and doing inspections and not changing out components, putting something else in there. Finally, considering the result of the FMEA, including presentation of the risk accepted rationale, the system safety analysis in this example is in the position to provide an accurate, well-considered, and probably properly evaluated recommendation to management to accept the level of risk associated with the use of this piece of equipment. It's highly unlikely, 1.67 in a million chances that this piece of equipment is going to fail, especially considering all of these things that they're recommending with the daily inspections, weekly inspections, annual inspections to make sure that it is operating appropriately. And that is the end of the FMEA. Any questions?